Hi everyone, this is your host Amir Jafari. This is the first lecture in a series of lectures on magnetic reconnection. In the introduction, I gave you a very simple definition for magnetic reconnection, which is if you have a plasma or electrically conducting fluid in general, but usually it's a plasma. And what's a plasma? Well, it's a fluid with ions and electrons, so it's electrically conducting fluid. So you have this plasma, you have magnetic field inside that. It's a magnetized plasma, and magnetic field evolves. It has some own, some dynamics, but that dynamics is related to the dynamics of plasma as well. I mean, there is this interaction between plasma and magnetic field, the velocity field and magnetic field, if you like. So magnetic field is not like living alone; it's interacting with plasma. So it makes the problem more complicated, obviously, but it is what it is. So you have this magnetic field evolving in time inside the plasma, and then sometimes all of a sudden, in some region of plasma, you see a sudden change in the pattern of magnetic field. So magnetic field releases some energy, relaxes to a lower energy state, and magnetic energy is converted into kinetic energy of the particles. Plasma is kind of ejected from the reconnection zone where magnetic reconnection occurs, and also heat. The reconnection heats up the plasma, and even if you start with a plasma which is kind of in a laminar motion or at rest, say, because of reconnection, you're going to get very chaotic, fluid motions. So you're going to get turbulence there. So this is the reason we have to consider the role of turbulence on magnetic reconnection. And usually, what you see in astrophysical environments, especially, is turbulent magnetic reconnection. In this lecture, I'm not going to talk about turbulence. We'll talk about simple magnetic reconnection and simple notions and concepts related to that, some terminology, what's reconnection zone, what's the current sheet, stuff like that. And in the second lecture and so on, we're going to study the role of turbulence, magnetohydrodynamic turbulence. If you don't have a background in the theory of turbulence, it's okay because we're going to borrow some notions, some tools from there, but we're going to explain them and we're going to learn those concepts before applying to reconnection theory. Okay, let's just start with a very simple picture. Okay, what's the simple picture? Let's begin. By the way, let me share my screen here, my iPad screen, so you can see what I write here and what I draw here. Okay, to begin with, let's imagine you have a magnetic, well, what's going on? Okay, right. Imagine that you have a magnet, okay, a simple magnet like this. So you have magnetic field lines. This notion of magnetic field lines introduced by Faraday is a very useful concept. I try to be kind of symmetric here, so my drawing is not that bad, but on my iPad it's not very good. So, but you get the point. From N to S, so other field lines are here, something like this, right? This should be familiar from, I guess, elementary school. I remember in elementary school we had these experiments with magnets where there was a piece of paper. Under that, we would put a magnet like this, and above that, on the paper, we would put some iron filings, I guess. So you would see some patterns, some beautiful pattern of this sort on the paper, iron filings. So these imaginary lines are magnetic field lines. I'm going to argue in the future lectures that these are very, this notion of magnetic field lines is very useful in electromagnetism, many problems related to magnetic fields. But in magnetic reconnection, in plasmas, especially turbulent plasmas, which are what we have in astrophysical systems, these are not very useful, and the notion of magnetic field lines is a source of confusion and misunderstanding. We'll talk about this, but for now, let's stick to this notion of field lines, and we'll be fine. Okay, so what you have here is a pattern. This is what I mean by a magnetic pattern. I'm not going to give you any mathematical, definition here. Although in the future we're going to talk about topology of magnetic field and topology of, magnetic trajectories, field lines, etc. But for now, this is what I mean by a magnetic pattern. You have a pattern here, okay? So that's it. This is the concept of field lines. This is what I mean by a pattern. What you have here is a stationary state, right? A stationary state in the sense that if you sit down here and stare at this magnet for centuries, nothing is going to happen, right? These are kind of, static field lines sitting there, and you are looking at a kind of, non-dynamic thing. Although at the small scales in the quantum world, there's a lot happening, but classically this is a simple system, nothing very interesting. So, and especially reconnection cannot happen here. Okay, why? Because for reconnection to occur, you need something like this, a configuration, not like this one, a pattern for magnetic field, not like this one, but with a strong shear. You need a situation, a pattern for magnetic field, which is something like this. As is always the case in physics, of course we are idealizing this problem. In a plasma, you're not going to see anything like this, a simple situation for magnetic field. It's going to be more complicated, okay? And we're going to talk about this complexity in the future as well, very briefly. But you can get the gist. You can get the from this idealization, you can understand what we mean by magnetic reconnection, and then we can add more complexities and more details to build up a more realistic model. Okay, and one more thing. When I draw something like this, and I call it a piece of plasma, this is a region of a plasma, a highly conducting, electrically conducting fluid. What I mean is not a two-dimensional system. I'm talking about a three-dimensional system. Remember, magnetic reconnection is a three-dimensional process, okay, in general. So when we draw cartoons like this, we don't, mean that we are working with a two-dimensional system. No, because for simplicity, we draw pictures like this, assuming, for example, in this case, that there is a perpendicular component of magnetic field perpendicular to the screen. It's called the guide field. But the primary reason that we have this sort of two-dimensional drawings and cartoons is that, well, my iPad screen is two-dimensional, your computer screen is two-dimensional, so we have to deal with it. When we draw something, it's two-dimensional. But reconnection in general is a three-dimensional process, especially in astrophysics, real astrophysical flows that we are interested in this series of lectures. All right, so what you have here is a magnetic field, a pattern in which you have some shear. You see these oppositely directed magnetic field lines. Oppositely directed magnetic fields are kind of touching each other. At this, let me change my color. In this region, okay, and I can highlight it for you, you have a strong shear. Shear means that you have two layers of fluid with different velocities or different magnetic fields. In this case, we are talking about, a layer in red font here, in red color here, and above that you have another layer with magnetic field directed to the right, and below that you have magnetic field oriented in the opposite direction. So this is what we mean by magnetic shear. So you have a strong shear in this region, and when you have shear, then it means that you have a strong electric current for magnetic field. When you have strong shear, it means that the curl of the magnetic field in general, the derivative of magnetic field with respect to position, is strong. So in this region, you have a strong electric current. So for that reason, this is called a current sheet. It's a sheet because it's kind of thin, little delta, capital delta. So capital delta is much larger than small delta. So it's kind of a sheet, and remember, this is three-dimensional, so you have to imagine we have something like this, in space, in three-dimensional space. So it's a sheet where we have a strong current, so current sheet, okay? Now, what happens? Well, this situation is kind of unstable, right? Magnetic field doesn't like this. You have a strong shear, you have a strong electric current, and that means that the Lorentz force, which is J cross B, can be very, very large in this region of plasma, okay? So, as a fluid, plasma doesn't like the situation. It wants to get rid of the shear, get rid of these strong, magnetic, Lorentz forces, and to relax to a more stable situation. So you can put it this way: magnetic field would like to relax and go to a lower energy state whenever you have this kind of situation, this kind of shear. Okay, so what happens is something like this. The plasma and magnetic field lines, if you like, move in this direction and also in this direction in this simplified picture. But this is basically what happens with some velocity. Let's call it VR, reconnection velocity, VR. And because of the conservation of mass, well, the plasma cannot be destroyed. When you push it this way and this way, it's going to be ejected from these sides. So to get a prettier picture, let me change my color again. From here, you get a different velocity, ejection velocity, if you like, which is VA. What is VA? VA is the Alfvén velocity, which is basically magnetic field divided by the square root of density of plasma. Depending on the units you are working with, SI, Gaussian, whatever, there's going to be like 4 pi's, mu's, etc. in these equations. And this is the reason that I don't use, I'm not writing equations here. I use this, scaling notation. So we can, work with, any unit you like, okay? So these are general expressions. We are not worried about the, precise numerical values, so I'm gonna ignore those constants. But in any, real calculation, we're gonna, choose a unit of a system for units, and then we have to worry about these constants, etc. But for now, we're okay. So the Alfvén speed or velocity is magnetic field divided by the square root of density. This is the ejection velocity. And the problem here, one problem, is to estimate this reconnection speed. With what, velocity speed this pushing happens, the pushing of plasma to reconnection zone. You can call this area the reconnection zone. Zone or region of plasma where magnetic reconnection occurs, and this process is called magnetic reconnection. It's usually very fast. So although you have kind of stationary reconnection models as well, but in general, in many situations, in accretion disk, in the solar wind, etc., you have this reconnection event as a rapid, fast event, fast process. So what you see is something like this. You see evolving magnetic field lines, approaching. It takes a while. You have some dynamic here, but all of a sudden you see something like this. happens. So field lines, if you are interested in field lines, will can be thought of as disconnecting and reconnecting. Although I'm not a big fan of this, I think mathematically it's inconsistent, and I'm going to talk about this. I think in reconnection problem, in the evolution of magnetic fields in magnetized plasmas, turbulent plasmas, I think you shouldn't use the notion of field lines for various reasons. We're going to talk about this, but for now it's okay because we are, trying to provide a primitive picture here. So what happens is these field lines are kind of disconnect and reconnect. So in this region, I have magnetic field oriented in this direction. So you have these field lines. Above, I have this direction. So you see that outside of this reconnection zone, the direction of magnetic field doesn't change much. But here you see initially you have these arrows, field lines in green font, green color, and then they all of a sudden change, and you get this pattern in red color. This is called reconnection. Okay, so here if I use the same color in the opposite sense, I guess, right? Let me. What else I have here? Let's use blue. Okay, so these field lines will reconnect and become something like this. Okay. This is that. And here we can draw it this way. And remember, this is just a simple drawing to provide you with some, visualization or imagination of what's going on. But in reality, it's more complicated, the geometry, everything. But this is what we mean by reconnection in general, okay? So when this happens, this connection and reconnection of field lines, so the name reconnection, you have this ejection of plasma from both sides. And the problem is estimating this reconnection speed, okay? This is one problem. Now, how can we solve that? Let me draw another picture. So we have something like this, and this is the current sheet, delta, delta. Okay, so here you have VR, VR, VA, VA, and this is your current sheet. Okay, so first of all, we have this conservation of mass. Okay, in this two-dimensional, not two-dimensional problem, but two-dimensional view, you can write down the conservation of mass in terms of these quantities as VA times delta. This is delta, the thickness of the current sheet, and from there you have this velocity VA, ejection of plasma. So this should be equal to VR, this is the plasma which is kind of pushed into the reconnection zone here, times delta. And we are, for now, ignoring this, the third dimension of the current sheet, because we are assuming that there is a guide field and what's going on in the dynamics is important in just these two dimensions. Okay, this is conservation of mass. This has nothing to do with electromagnetism, Maxwell's equation, etc. This is just, simple physics. But we have some, other information here as well. In order to get VR. From here, VR would be, well, VA delta over delta, okay? You can measure VA, alpha in velocity, because as I said, VA is just B over square root of the density. Density is known, you can measure it. B is known, you can measure magnetic field using, for example, the Zeeman effect, etc. So we can have access to this, these data. But what's unknown in this equation here is delta, little delta. It's hard or sometimes impossible to measure the thickness of the current sheet. What do you mean by that? It's kind of theoretical thing. And as I said, in real world, in real astrophysical systems or in laboratory plasmas, the situation, the configuration would be more complicated than this picture here. So we don't know little delta. How get little delta? Well, the other information we have is about the current, right? Electric current J is given by this formula. Again, I'm not choosing a unique system of units here. If you're using SI, Gaussian, whatever, you have to worry about different constants. But here we are talking about scaling laws, and in fact, I will use instead of equality some notation for scaling. So we are estimating the reconnection speed and other quantities here as an order of magnitude estimate. We are not talking about precise values, okay? So this is your J, and also we have the Ohm's law. In a plasma, it can be written, for example, this way. Okay, so this is the information we have from magnetohydrodynamics, from plasma physics, if you like. These are elementary concepts, so I'm assuming that you're familiar with these, because if you're interested in magnetic reconnection, so the assumption is that you are familiar with basic concepts from plasma physics and magnetohydrodynamics, so I'm not going to explain them, but maybe later in the future we will have a series of lectures on magnetohydrodynamics or plasma physics, I don't know, but for now I'm assuming that you are familiar with these equations. Okay. So as an order of magnitude estimate, you can write this as J. The sign means that we are talking about scaling laws, order of magnitude estimates, not precise values. B over delta, because remember, curl mathematically means derivative with respect to position, and here the spatial distance on which magnetic field changes, there is shear there, is this little delta, okay? The oppositely directed magnetic field lines, the magnetic field changes in this layer, on this distance delta, so curl should be, again, as an order of magnitude estimate, B over delta, thickness of the current sheet. Okay, that's J. And from here, you know that the electric field is kind of negligible in a plasma because of quasi-neutrality condition. And V here is the flow velocity, the velocity with which plasma moves. B magnetic field, eta is resistivity, J the electric current. So from here, you get V, my notation would be VR, okay, VR B eta J. Okay, now you get these two relations, and if you combine them, what you get is VR B eta instead of J, you have B over delta. You can get rid of B's. VR is eta over delta. Okay, so you get this estimate for VR from electromagnetism, from plasma physics, from here, and conservation of mass gives you another relation for the reconnection speed, which is here. So this is relation 1, this is relation 2. So by combining them, what you get is VR eta over delta, and if you substitute delta from the first relation, you're going to get VA over delta, I guess, square root. Okay, so this is what you get for the reconnection speed. Okay, this is what you get. Eta, again, resistivity, VA of wind velocity, delta, capital delta, is the length of the current sheet, or almost the reconnection zone, so it can be measured in practice. So we know, for example, in the solar corona, what is delta. When reconnection occurs, we can have access to this information. What's capital delta, the length of the current sheet, what's alpha velocity, and eta resistivity can be measured as well. So we can get VR. But the problem, by the way, this model, I didn't write, exact equation. It wasn't a rigorous calculation, but overall, it's a physical model. I didn't want to actually delve into mathematical details. It is what it is. This is what you get for the reconnection speed overall. This is called Sweet-Parker reconnection model. Parker, I guess, developed this model in a series of papers, I guess, but the first one was, if I'm not wrong, 57, and this was 58 in a conference somewhere. So this is called Sweet-Parker, the Sweet-Parker model, okay? This is called the Sweet-Parker model or the Sweet-Parker reconnection speed. Now, what's the first thing? When you have a theory, what's the first thing to do? Well, go to the lab or an observatory and look at the data you have from observations or experiments. This is the job of a physicist. Experiments. This is the final, judge. Experiments and observations. When we compare this reconnection speed with observations, for example, observations of the solar corona, we see that this is hopeless. This is orders of magnitude slower than what we see in the solar corona. So there is no hope for this model to work and to predict something real in real astrophysical systems. So the question is why? Why this model doesn't work? We are basically we use Maxwell's relations, kind of, the definition of the current, Ohm's law, the basic things from electromagnetism, and also conservation of mass. So these, concepts should be applicable here, because if reconnection is what we see here, what we imagine here in this simple picture, or something like that, this should give us some right estimate, at least as an order of magnitude estimate. Why it's not the case? Well, since then, starting, I guess, in 1960s, many years ago, people started to think about this problem. Why the Sweet-Parker model doesn't work and is not compatible with observations? Well, there have been suggestions. There have been remedies. For example, one of them, I'm not gonna, go into details of these models because I think they are not important. We'll see why. So just to mention a couple of names, there is this X-shaped pitch-shake geometry, assuming that instead of, if you have reconnection like this in the Sweet-Parker model, it says that no, instead of having a current sheet like this and reconnection zone in this form, what is going on is something like this. Okay, so magnetic field lines move in this, manner, and you have a kind of X-shaped geometry. And X-shaped geometry means that you are basically working with a smaller delta, capital delta for this. So this was the length of the current sheet. By making it smaller and smaller, it's in the denominator here, you get a larger and larger velocity. So this is one remedy, for example, one of the oldest. And then there are other processes that can, in principle, affect reconnection, making it faster than what Sweet-Parker reconnection model predicts. For example, Bohm diffusion, different instabilities like tearing modes, the Hall effect, etc. Some of them, for example, add terms here. Okay, add terms, different terms to the Ohm's law, saying that, well, we have these extra terms, different, processes, and in this way you can, make the speed faster, compatible with the experiment somehow. And there has been research on this, different processes, different instabilities, especially in plasma physics communities. And there is ongoing research. You can look up, there are papers published, highlighting one or two of these processes, from instabilities to different diffusion processes, etc. But at least in astrophysics, we know that these processes, which come from small-scale plasma effects, for example, the ohmic resistivity here is a small-scale thing. It's the collisions actually between particles at small scales. These processes cannot affect reconnection in a major way. Okay. In the second lecture, I'm going to show you this this fact mathematically. And what is important is the role of turbulence. Turbulence is this superchaotic motion in the plasma. So if here you have turbulence, if the plasma is turbulent, what you would get would be something like this. For magnetic field lines, well, this is a very primitive cartoon, but you get the idea. Instead of those smooth magnetic field lines at any moment time, you get something like this. Okay. So, and in 3 dimension, they can kind of, entangle, right? So it's much, more complicated than what the Sweet-Parker model assumes. I mean, it is doomed to fail in the outset, because when you draw a picture like this, you're assuming that the plasma is kind of at rest. It's kind of, in a laminar motion in some coordinate system. So the flow is laminar. Technically speaking, we say that you're assuming here the flow of the plasma is laminar. There is no chaotic motion, there is no randomness. This is not the case in, for example, the solar wind. It's super chaotic. Remember, as I said before, I guess in the introduction, turbulence is more chaotic than simple chaos. We're going to talk about chaos, we're going to talk about turbulence and difference between these two. But for now, turbulence is just super chaotic motion in the fluid. So when you have turbulence, you can't draw like smooth magnetic field lines like this. You have to consider random components in the magnetic field, random component of the velocity field. Interaction becomes tricky and subtle between velocity field and magnetic field. So this picture shouldn't be expected to be compatible with reality. So, as I said, the next thing I'll do in this second lecture is to show you, to provide some calculations, or to provide some intuitive picture before calculation, before doing any calculation for turbulent reconnection. Show you that what kind of effect the turbulence can have on magnetic reconnection. Overall, physically, this is what you get, a very chaotic system, but we can make this mathematically more precise, and we'll do this in the second lecture. But to end this picture, let me derive this Sweet-Parker result in a very different way, which is going to be useful when we talk about real turbulent magnetic reconnection. By real, I mean what you see in astrophysical systems, also in laboratory plasma. Okay, again, you have something like this. For now, let's ignore turbulence. We're talking about Sweet-Parker model. Okay, this is delta, the thickness. This is capital delta, the length of the current sheet. And what you have here, you think about the induction equation. Okay, induction equation is something like this. right? Plus, I always forget, is this a plus sign or minus sign? I guess it's a plus sign. So V is the velocity of the plasma, the velocity field. B is the magnetic field, eta resistivity as before. So this is the induction equation. Again, I'm assuming that you are familiar with this because this is the an elementary, concept from magnetohydrodynamics or electromagnetism. Okay, so if you are talking about the diffusion of magnetic field, these two terms are important if you are trying to get a time scale for diffusion, okay, the resistive time scale, so to speak. So from here you can say B over T, order of magnitude estimate, again, eta B over delta square. Laplacian of magnetic field means second order derivative with respect to space. And the magnetic field changes here on a scale little delta. So Laplacian would translate into B over delta square. So from here, you get a time scale, the resistive time scale, the time scale for the diffusion of magnetic field, which is at an order of magnitude, estimate. Okay, and from there you can get delta. Delta is eta t. Okay. So you can call this TTA, or whatever. I guess in my notes I called it just T. So this is the resistive time scale. So this is delta, and on the other hand, what is T when you have reconnection? Well, as I said before, red color VA, the Alfvén speed. Plasma is being ejected with some velocity VA, Alfvén velocity. And this is, remember, delta, this length scale. So how long does it take for plasma to travel along this current sheet? T should be something like delta over VA, order of magnitude, right, when reconnection occurs. So these two time scales should be comparable. So you can write this relation as, now instead of T, I have delta over VA, right? So I got delta. So on the other hand, again, I have conservation of mass. Here you have delta. So delta VA should be of order delta VR, mass conservation. Okay, VR, plasma is being pushed along in this direction perpendicular to current sheet, and this is the length of the current sheet. So VR times delta should be equal to VA times little delta, the thickness of the current sheet. And if you combine now these two, 1, 2, you get the same result. From here, VR, you get it eta over VA over delta. Sorry, little delta, big delta, capital delta. Okay, so this is the same result we got before. Okay, the Sweet-Parker connection. So if you think about the diffusion of magnetic field, just normal diffusion, resistive diffusion, diffusion by resistivity, you get the same result as we got before using other concepts here, the current, and the Ohm's law, etc. So it looks like a consistent picture. So we didn't do anything wrong. I mean, in terms of calculations, there was no typo, something like that, or wrong sign. No, the physics, is wrong in a very, basic way. It's not an incorrect calculation, for example. So because both ways you get the same result. So what is wrong? As I said, in principle, there are many other processes like the effect of instabilities, the Hall effect, etc. But it turns out, and I'm going to talk about this in some length, that what's wrong with this model is that you are assuming the flow is laminar. Instead, you should have field lines like this, very chaotic. The magnetic field has a large random component because of turbulence. And that random component, behaves in a chaotic, stochastic way. So you have to think about stochastic field lines, random field lines, stuff like this. So it gets more complicated. But the good news is that turbulence seems to make the process of magnetic reconnection more complicated, because turbulence is a complicated problem in general. However, I think the good news is that turbulence also makes reconnection much easier and simpler to understand and deal with, because the presence of turbulence will let you get rid of all those processes coming from, small-scale plasma effects. Like, you don't have to worry about both diffusion, carrying modes, different instabilities, X-shaped geometry, stuff like that. Forget about all of them, because they are small-scale effects. In the next lecture, I'm going to show you some kind of, in some mathematical form, that if you take into account the role of turbulence, you'll see that all other terms in the Ohm's law, for example, are subdominant. It's been shown rigorously in different papers. We'll talk about them. And what remains is just turbulence. And the effect of turbulence is not that complicated to understand. I mean, you can understand it using some methods from condensed matter physics and quantum field theory, known as renormalization group. We're not gonna, study renormalization group theory in its details as it's, for example, applied in particle physics. But a simple procedure of coarse graining, averaging the equations, would suffice in this case, and you'll see that you get a nice picture for magnetic reconnection, which is compatible with observations and numerical simulations. Okay, it's called turbulent magnetic reconnection, and it's the subject of a couple of lectures. Next one, and I guess a few more lectures after that, we have to talk about turbulence and also the role of turbulence on reconnection, and then develop this model of turbulent reconnection, which was, by the way, discovered in 1999 by Alex Lazarian and Ethan Vishniac. And we're going to talk about this reconnection model. We're going to talk about different, approaches you can have to understand this model. You can use field lines, as originally was done by Alex and Ethan in 1999. You can talk about, spontaneous stochasticity, as Gregory Eying did a few years after, discovery of turbulent reconnection, stochastic reconnection. And recently, I've also argued somewhere, I'm going to mention this in the maybe the last lecture in this series, you don't have to work with field lines, and you can have a very simple and new approach to turbulent reconnection using magnetic path lines. But this is for the last lecture, I guess. So that's it. This is the second lecture. I guess it's time to wrap it up. In the second lecture, we are going to talk about the role of turbulence and start our discussion of turbulent reconnection.